Hello, welcome back to the Geography 300 Geographical Data Analysis video series for WVU. We are continuing our discussion here of regression concepts. So, we saw in the previous, previous video, this introduction of basically what regression is measuring and how it is working. I'll now especially put that prediction idea into context here. So I will start with a scatter plot. And our two axes for our scatter plot are the independent variable, or x, always on the horizontal axis. Our dependent variable, always y, always on the vertical axis. And we can go and put in the points. So here I put in a set of points onto the scatter plot. What regression is doing, and this may kind of bring back flashbacks or repressed memories, whatever, of high school geometry. Regression is then going, I'll start with the geometry version, putting a line in here. What you will see is often called linear regression. I'll start with the equation and then I'll draw the line. Remember, one of the forms of writing out a line, slope-intercept form, you can have y equals mx plus b. This is what we use basically. But it's then saying y equals instead of using m, we use the Greek letter beta. In place of b, you'll sometimes see beta subscript 0 or beta naught, or something else to represent what's called the intercept. You can still think of this as the slope. It often gets called, though, the coefficient. And so we have our coefficient, we have our intercept. So we get this line. Now this is not just any line for regression. And beta 0 is indeed where that hits the y-axis, just like the intercept and slope-intercept form. Sometimes that's useful for us in interpretation, sometimes it's actually not useful for us. That goes on a case-by-case basis, depending on, does it really matter what the value of our independent variable, or what the value, when our independent variable is 0, what is our dependent variable? That may be of interest, that might not. And then we go from there. If I change x by 1 unit, if I increase x by 1 unit, what happens to y? That is beta, so the slope of the line. As I said, this is not just any old equation. This is, it so happens, in a particular sense, the best possible line to represent the data in the scatter plot. And how we get to that idea of the best possible line is we actually want to understand what the errors are. Just as we're interested in chi-squared, what's the amount of error in our prediction? As I said, in regression, we can treat this as a prediction. Okay, what then, how good is our prediction? Well, for any value of x, so if, I'll just put 5 here, if x equals 5, here's our predicted value. I go up to the line where x equals 5, and then I come over. And I am saying this prediction, I'm representing it as a prediction by putting a hat over y, which means really, for this regression line, I need this hat to be very clear about what's going on here. But I have a value here for this point. That's actually not, so how much error, here's what it should be, but here's where it is. So where that happens, y is not the same as y hat. Most of the time, it's not going to be the same. We can think of that as the amount of error in our prediction. It often gets called the residual. So what this puts here for our prediction is our actual value is our predicted value plus that residual. The residual is something that will be coming up, we'll be interested in, and we'll be wanting to look at the residuals throughout. So, okay. You may or may not have come across something called sum of squared errors, or the idea of OLS as an acronym for this kind of regression. Ordinary least squares. What's common there is the squares part. Now, okay, you might be thinking, okay, if I want to see how much there is here in terms of error, okay, if I just add things up, plus or minus the residuals, well, sometimes they're above and sometimes they're below. In this one, my predicted value was too high. If the predicted value is too high, I need to have a negative residual to get to the correct value. So epsilon must be negative. In others, it's the other way around. Epsilon must be positive. We don't want those to cancel each other out. We then, and the other thing, which is somewhat more esoteric, is even if I just put an absolute value of, so the distance of this error, as opposed to paying attention to is it above or below, even then I could have multiple values that are equally correct. Multiple lines with the same sum there. So what, instead of absolute value, what we use is we square this residual. And we don't need to, we're not actually going to deal with the squared residuals. We're going to basically let Excel or ArcGIS or Geoda handle all of the computations, the calculations for us. But so I have here, I find the difference, the error, and I square that and add everything up. That's what this sigma means. It's summing up for all values. Or all points, all observations, all points in the scatter plot, which is our observations, whether they're points, polygons, what have you, or even not tied to any geometry. Find how much error there is, find that residual, square it, add it up. The sum of squared errors. Our regression is the line that has this particular representation of the total error minimized. So in that sense, it is the best possible regression line, the best possible representation of that relationship, or providing the best possible predictions across the entire data set. So then, the kind of the last thing here, we are going to get a couple pieces of output. We get this beta, we get our intercept, we get one more piece of output called r squared. Which we can say is the overall goodness, so to speak, of the relationship. R squared, it ranges from 0 to 1. 0 means terrible relationship. There's no predictive power whatsoever. 1 would mean perfect prediction. Every single black dot in the scatter plot lies along the red line. Absolute perfect prediction. R squared of 1. Most of the time we get something in between. And what that would end up representing, so for some people, just sticking with the goodness of the relationship may be the best for helping to understand what R squared is doing. In a more specific sense, especially relating it kind of to ANOVA. So we're in ANOVA, we were looking at how much of the variance in all of the points is related to the variance within the group versus variance between the groups. If there's a lot of variance between the groups and not much variance within the group, we had a strong relationship. We could use our groups to really understand the variation in this sense, our dependent variable. In regression, it's saying how much of the variation in the dependent variable can be explained by the variation in the independent variable. If there's no relationship, then 0% of the change in the dependent variable can be explained by this independent variable. A perfect relationship, then all 100% of the variance in our dependent variable can be explained by our independent variable. As I said, most of the time it's in between. We might say an r squared of 0.5. Okay, that means the variation in our dependent variable, half of it, 0.5, 50%, can be explained by changes in the independent variable. As it gets bigger, as it gets smaller, and the other half of that variation in this dependent variable is explained by something else, something that's not part of our study. Whether or not 50% is good enough for you, is a good enough fit, that's up to you. And we'll kind of put a little bit more on this in the next video when we see putting this into our inferential statistics, inferential hypothesis testing framework, and basically bring in p-values to this discussion of the coefficient, or the slope, the intercept, and r squared. So that is the nuts and bolts, so to speak, of a lot of what you will see as output in regression, and some of the things we may be interested in looking at for making our decision, for deciding if we have a true relationship or not. As I said, we'll build on this in the next video, putting it into the inferential statistics framework. But as always, if you have questions, please contact me in class, by email, however. And as I said, if you have questions, let me know. If not, thank you for watching. I will see you at the next video.